Good afternoon. I'm Panos Galanis, and I would like to present you the work I'm doing with my research advisor, Professor Jack Maley. The focus of my research is the seismic behavior of existing reinforced concrete buildings. And today I would like to present you how OpenSees could be utilized for the seismic assessment of existing reinforced concrete buildings. So before I proceed, let me guide you through my presentation. So initially, I would like to give a brief introduction of what I'm doing. Then I would like to provide an overview of the methodology. And then I would like to show you how OpenSees could be used for the seismic assessment and give you also an example of this. So currently, the main documents that are used for the seismic evaluation of existing buildings are ASCE 31 and ASCE 41. But both documents have certain limitations, and some of the main limitations are that the current codes do not determine collapse risk. Secondly, they don't address the relative importance of specific deficiencies, and overall, we are very conservative in selection of modeling parameters. So also the seismic evaluation is conservative. So my work is partially funded by FEMA under the ATC 78 project. And this project deals with the assessment of collapse risk of non-ductile RC structures of buildings that are representative, that are constructed between 1950 and 1975. So these are buildings around 1970s. These are considered buildings that are very, very dangerous, especially in California. So the main objectives of the current study is to understand the relative importance of common structural deficiencies. Secondly is to introduce a systematic framework, probabilistic framework, to determine the dynamic response of all buildings. And the final product should be to reduce the conservative in assessment and hopefully to help in the retrofitting of old structures that currently is very costly. So to start, the method starts with selection of a specific of one building. So we have under this method we have looked at several buildings, but this is one of them. So we started by looking one building that was designed by us, and it's designed like a new building, so it suffers from no deficiency. And this is one building that we looked at. It's a 6-story, 5-bay frame. So the idea of the method was to start with a benchmark building. This building is designed, as I said, like a new building and suffers from no deficiency, and starts gradually and gradually introduce specific deficiencies, run many dynamic analysis, and so we are selecting a set of ground motions, and here you can see these are incremental dynamic analysis curves. So basically we are scaling the ground motions, and each of these curves corresponds to one earthquake. We're doing statistics, and we are getting what is called nowadays fragility curves. In the x-axis, there's the intensity measure, which is the spectral acceleration, and in the y-axis is the probability of collapse. So by these curves, we can assess and we can understand what is the effect of specific parameters in the dynamic response, and compare what is the probability of collapse. Please note that we are using the term of probability of collapse, but this is approximate. Like, there are many uncertainties that we do not address. but practically we are seeing probability of collapse as a measure of performance. So this methodology covers a wide range of issues, and there are many challenges. So the first challenge has to do with a simulation of collapse. And the first issue with simulation is the modeling of deterioration of structural members, which is a difficult issue. To make things even more complex, all buildings suffer from brittle type of failures like shear or axial failure, which are very hard to model. And finally, when a structure is subjected to extreme loads, like an earthquake load that leads to collapse, there are nonlinear geometry effects coming from large displacements that should be addressed. So another challenge of the methodology is the time efficiency. So many dynamic analyses are required in order to do a proper statistical assessment of the seismic behavior. So we need to optimize the time that it takes to run this dynamic analysis. Finally, this method tried to introduce a probabilistic framework to evaluate the collapse risk of the structure. So to become more specific, let me give you some of the main modeling assumptions. So we are assuming that the building that appears here consists of 6 frames. All of them are considered as capable to resist earthquake loads. So practically the earthquake's mass is equally distributed to the frames. The building the configuration of the building is very simple. So 2-dimensional dynamic analysis was performed. There are no torsion issues because of the symmetry of the building. The lump plasticity approach was utilized to model the nonlinear material behavior, and P-delta effects were considered to take into account the nonlinear geometry effects due to the large displacements. The elastic stiffness of the members was modified according to the ASE 41 code to take into account concrete cracking and bar slip. Finally, the joints were modeled as rigid, and currently the failure of joints is not taken into account. It's planned, but not yet. And they are modeled rigid according to ASE 41. So the first challenge was the simulation and modeling of structural collapse. So for the cases that collapse is controlled by flexure, as I said before, we used the concentrated plastic hinge model, and we used the clough uniaxial material for the behavior of the springs that are located at the end of the column members and the beam members. And this uniaxial material has the advantage that it has this post-capping negative slope that allows us to simulate collapse and deterioration of structures. And this is the backbone curves. So there are several parameters that should be defined, and these were defined according to Hasselton, Dirlein et al. So Hasselton and Dirlein took a sum of tests in columns, and they tried to fit the results. So their clough material, as modified by Ibarra, is taking into account cyclic strength deterioration. So this is deterioration that the structure experiences before it reaches to the capping point, so in this range. And there is the in-cycle deterioration that is coming from the post-capping negative slope. The other issue is structures that failure is controlled by shear or axial failure. And this is very typical of all structures where the transverse reinforcement is very wide. The structures suffer from this type of failures that are very brittle. And to model shear failure, there is the limit state uniaxial material, which is developed by Elwood and Maley. So this, to model the shear failure, two springs, a shear and an axial spring, were introduced in the column members at the top of the members. The limit state uniaxial material is a complex material. So what this material does is that it tracks the displacement and the interstory drift of the column member, and there is a relationship that is predefined that relates the force with the drift, and this is practically a surface, and when the force lies inside the surface, then shear failure is not initiated. But when the force goes outside this surface, then shear failure is initiated. The same happens with the axial spring. Practically, there's again one relationship that relates force, the axial force, and the drift. And when the axial force is higher than the limit, then axial failure is initiated. So regarding the dynamic analysis, a set of 44 ground motions were selected. This corresponds to far-field records. And this is the same database that the FEMA P695 project used. We select the same ground motions so that we are consistent with this study. This study corresponded to new buildings. So we hope that this would be helpful in terms of comparison. So to avoid bias of results, no more than 2 earthquakes were taken from any earthquake. And the ground motions were scaled to increase the earthquake intensity so that they lead the structure until collapse. Practically, the procedure we are following is very similar to the incremental dynamic analysis. And one issue is how collapse should be defined. And one way that we define collapse is if we are practically considering 2 modes of collapse. One is the side sway collapse. This was defined by a high value of interstory drift. Like if the interstory drift was higher than 10%, so we defined this as collapse. And some of you might think that 10% is a very, very high number. But practically, I would say that after 6 or 7%, like the IDA curves are practically flat. So that number really doesn't matter. It's a big number, but it's selected so that we are sure that the IDA curves are in their flat plateau. So when the curves are in this plateau, it means that the structure practically has no resistance. The other mode of collapse that we selected was the vertical collapse. So this is happening practically when the axial spring is failing. And the vertical collapse was defined when more than 50% of the column members in one story have started failing in axial failure. So the probability of collapse after this was calculated for different spectral acceleration levels. We hope that the engineer would be able to select what spectral acceleration level would like to consider. So to perform this dynamic analysis, both OpenSees and MATLAB were used. OpenSees was used as the software to do the dynamic simulation. And MATLAB was also used in order to modify OpenSees script during the analysis. And this was great because it gave us a lot of freedom to do the to do all this analysis in an automated way and to help us optimize the time of this analysis. So practically, this MATLAB routine helps us in scaling of the ground motions. It allows to track collapse in real time and so modify the scaling. It also helps to modify the solution algorithm in real time. And I will show you some more about this later. And finally, a post-processing of the results was performed. And this is to create these fragility curves and assess the collapse risk. So to define the ground motion intensity, we use the spectral acceleration, which is recorded on the fundamental period of each of the studied buildings. As I said before, we're using practically the incremental dynamic analysis method. So the intensity of the ground motion is scaled until collapse is detected. And I told you how we define collapse. So practically, we are using specific increments to scale the intensity of each ground motion. But after collapse is achieved, is detected, then we change these specified increments so that we can track the exact point that failure occurs. So regarding the solution algorithm, we are using MATLAB to modify the OpenSee's code, as I said, real time. And one issue that we experience running this analysis, because we are using like extreme loads to perform this analysis, that they lead the structure to collapse. As you understand, we encounter many convergence issues. So to perform this analysis, somebody needs to define the analysis time step, the solution algorithm, and the numerical tolerance. And if somebody starts with a very high analysis time step, probably he will experience very few convergence issues, but like in terms of computational time, the time increases so much that it makes the study not efficient, because we need hundreds of analyses in order to do this parametric study, because we are changing parameters, and for each of these, we are performing a number of dynamic analysis. So this code practically is changing the time step depending on if the error is smaller or larger than the tolerance. If this doesn't work, then this code goes and changes the solution algorithm. There are many options in OpenSee's, many solution algorithms that we use. And finally, if all this don't work, then we have to change to decrease the tolerance. But we set a limit for this, because after this the results will make sense. So if the error is like higher even for a very, very small tolerance, then we discard these results and we don't take them into account. So regarding the post-processing of results, as I said, we are having a set of ground motions. These correspond to far-field records. And these are the IDA curves that I'm talking about. So in the x-axis, I'm showing the maximum interstory drift ratio that occurs in each analysis. And in the y-axis, it's the spectral acceleration at the fundamental period of the building, of the studied building. And practically, each of these lines corresponds to one earthquake. And each of these points that you see are the results of one specific analysis. So we have a number of analyses, as you can see. Okay. So the statistical process of the results was, we did statistics of these results, and we have like something like an empirical cumulative distribution function. These are these points. So we try to fit a curve so that we have like a continuous curve so that we could assess the collapse risk for different spectral acceleration levels. And we selected log normal distribution, not because it's the best fit, but it's very popular among engineers. So the engineer is free to select to find what is the collapse risk for each different building for different spectral acceleration levels. And finally, we modified the collapse risk using the shape factor that. So to provide you an example of what we did is one major issue with all buildings is the effect of the transverse reinforcement ratio. This is practically related with the spacing of transverse reinforcement. So in the x-axis, we're having one parameter that it's the probable shear that one column member experiences over the nominal shear strength as defined by the ASCE 41. So this is practically like demand over capacity. So when the shear demand over capacity is low, then failure is controlled by flexure. And when it's high, well, then the members become like shear controlled. So like for its like VP over VN ratio, so for its like specific spacing of transverse reinforcement, we found what is the collapse risk for a specific spectral acceleration level. That in this plot we selected to be the maximum considered earthquake. So this is the spectral acceleration at the fundamental period of the maximum considered earthquake, and we can see the effect of how like VP over VN, like this parameter, is influencing the response. So finally, I think the conclusions is that OpenSees is a very powerful computational tool because it gives flexibility to the researcher to include because it includes a wide range of elements and materials. The second thing is it's an open source software, so it allows the user to go and modify the materials as he wants. And the last thing is that it has the advantage to cooperate with other software like MATLAB for pre or post processing of the results. Thank you.